Yeah.
Okay. All right. So this is a proposal of Dhruv Saxena. We have also committee members coming all over the world. So thanks to all of them for attending. And the format is that if you have any kind of clarifications, questions, shoot them. But if you have kind of more discussions, questions, please hold them to the end of the talk, and then we can have a conversation. All right, is that true?
All right. Just checking. You can. Everybody on Zoom can hear me and see the title slide. All right. Cool. Hello, everyone, and welcome to my PhD thesis proposal. I am Dhruv Mauria Saxena. I'd like to thank my committee for agreeing to guide me along the remainder of my PhD journey. So thank you to my advisor, Maxim Lipichev, and Oliver Kromer, who are here in person, and Chris Atkinson and the Matt Kroger joining us remotely on Zoom. And thank you all for attending and coming to listen to me. Hopefully, you learned something useful, and I'm going to tell you a lot of stuff about the things that will go into this thesis over the next year or so. The title of the talk is Simulation-Based Planning for Pick and Place in Clutter using Non-prehensile Manipulation, which is a bit of a mouthful. It has a lot of pieces to it, but we're going to build up to it, starting with a video that you're going to see of something that I hope that the robot is able to do. You're going to see the human reach into the back of the cluttered refrigerator shelf for a can of beer. But along the way, there's all this movable clutter that needs to be rearranged in order to make enough space to grab the can of Balzoberon, which is just an amazing beer. And if we want our robots to be able to do this, they need to know how these objects will move as it pushes them aside, because it might not be feasible to go and grab each one of them and put them down somewhere else. It's just more efficient to push them aside. And for that purpose, we need to know how they will move when the robot acts on. To do that, we include a physics-based simulator in the loop during planning. So if you do not use any physics-based reasoning, you could just ignore the other objects in the scene and try and grab the can of beer. But in that case, even if you succeed, you might inadvertently knock other things over, or you actually might fail to grab the can of beer in a lot of cases. Because there's no collision-free solution in a lot of these planning problems, you have to think about how these objects need to be rearranged under acceptable conditions, so that you don't make them fall over or fall off your refrigerator, but you still succeed in grabbing the can of beer. And the work that we've done in this thesis uses this physics-based reasoning while planning to come up with a sequence of actions where the robot figures out that it can push the can of coffee to the back of the refrigerator. It can then push the can of Spam aside, and then it's made enough space to go and grab the can of beer. And during planning, it's figured out how exactly to push these things aside, so that they don't violate any constraints that we've defined on how the robot is allowed to interact with these objects. So it'll grab the beer and come back out with it. But this domain of planning with a simulator in the loop for physics-based reasoning is what we refer to as simulation-based planning. And in our case, the task is that of pick and place in Clutter. So the robot is going to go and grab one object and come back out with it, all in the presence of other various objects in the scene. So I said this earlier, but most of the planning problems that we instantiate have no solution that just avoids collisions with the objects in the scene. You have to think about manipulating the environment and rearranging the clutter so that the task that you care about, grabbing this object of interest and coming back out with it, is achievable. But these movable objects, which are going to be in blue throughout the talk, have some constraints on how you're allowed to interact with them. So you can't just blindly push them aside. You have to be careful in how you do so, because at all times we ask the robot to satisfy these constraints. And I'll provide more details in the next section. But when you do manipulate this clutter and you're figuring out how I need to rearrange these objects to grab the one that I care about, you're going to end up with a multitude of interactions where the robot pushes an object, the object might push other objects, and you have to be able to evaluate the motion of these objects and how they're going to move when the robot is pushing something, so that your able to determine whether or not an action is valid with respect to the constraints you've defined. And for that purpose, we're going to use this physics-based simulator as our complex analytical physics model in the planning loop, which is super powerful because a lot of people have spent a lot of time developing these things, and they're able to very accurately tell you how the objects will move when the robot is acting in this environment. But that makes them pretty expensive to query because they have to integrate a whole bunch of physics equations over time to give you the result of any robot action in the scene. What we want from the simulator is to forward simulate the dynamics of interaction. So when a robot is, say, pushing this tall cuboid, I want the simulator to tell me whether it's going to fall over, it's going to hit something that's an obstacle that it's not allowed to hit. I want this information to be returned to me by the simulator. And suppose I just add a random object to the scene, then the same pushing action will now end up moving 3 different objects, and I need to satisfy constraints associated with each and every one of them. So I don't want to be the one sitting down to write the equations of motion of all of these interactions. I'm going to leverage the power of these simulators, but because they're expensive to query, because it can take a lot of time to get the result of these simulations, I need to be careful about when I ask them for a result of a robot action. And we focus a lot on rearranging this movable clutter via non-prehensile manipulation in our work. So non-prehensile refers to actions where the robot is, for simplicity, just pushing things aside instead of prehensile actions when it goes and grabs an object, which is the overall task that's been defined to it. In this example, the robot has to move a can of coffee aside in order to grab the box of cheeses, but the can of coffee itself is too big for the robot to grasp it. So pushing it aside via non-prehensile interactions actually allows us to manipulate things that are otherwise ungraspable. So we can manipulate larger objects, heavier objects, things that the robot might not be able to grab with these actions. In other cases, when there's more clutter and the robot needs to move aside the can of Spam and the mustard bottle to grab the box of Cheez-Its, it can be more efficient to rearrange the scene via non-prehensile actions, because one thing you could do is grab the can of Spam, pick it up, put it down somewhere else, come back for the bottle of mustard, pick it up and put it down somewhere else, and then go grab the box of Cheez-Its you care about. But our planners are able to find an action that just carefully nudges both of them aside at the same time while going for the box of Cheez-Its, because at the end of the day, that's the task we've specified for the row. It is to grab the box of Cheez-Its and come back out here. So in this thesis, we want to allow robots to complete complex pick-and-place tasks in the presence of heavy clutter. And we're going to use a simulator in the planning loop to evaluate the interaction dynamics of robot actions. Because it's very time-consuming to evaluate every single action in the simulator, we rely a lot on domain knowledge to tell us which actions are beneficial to evaluate in the simulator and when we should evaluate them. And this is going to come up in both the completed work, and I'll provide more details as the talk goes on. The problem on its own of simulation-based planning is difficult for 2 big reasons. The first is that when you start moving things around in your environment, you need to keep track of what state those objects are in. So you're not only searching in the robot's configuration space, which is X sub R here, but you also have to keep track of the configurations of the objects in the scene, X sub O's in this notation. So your search space for a solution grows with the number of movable objects in your scene. Second, to evaluate any action in the simulator takes much longer than just collision checking it, which conventionally has been the bottleneck for planning algorithms. But in this case, it does not suffice to simply collision check an action, because you need to make sure that if you execute that action, it does not violate any constraints associated with the objects. So for some of the actions that we use in our work, simulating takes 1.5 seconds versus only 30 milliseconds to collision check those actions. And this idea of planning among movable objects started in the mid to late 80s, where people would compute the whole configuration space and search for paths in this configuration space that they've computed offline. So if you have one robot and some movable objects, you can just geometrically compute the whole configuration space and then search for a path in them in that space. There was then work on non-prehensile actions, so using things like pushing objects or pivoting them, tilting them, toppling them to reorient them in a specific orientation for manufacturing purposes or for feeding them down a conveyor belt. And all of this was building on analysis that Matt Mason did on the mechanics of pushing in the late 80s. And then there are the two domains that are very closely related. And in fact, we focus on NAMO in our work, which is manipulation among movable objects. NAMO is navigation among movable objects. The difference is just in what the task the robot is assigned, and I'll provide more details in the next section. But 3 former PhD students have actually written PhD theses on these two domains. So it's a problem that's important for robotics, and I don't think we have a good solution yet necessarily. Part of NAMO is also similar to rearrangement planning, where the difference is that the goal for the robot is specified in terms of multiple objects in its workspace. So the robot is told that we have to move this bottle over here and this bottle over there and something else somewhere else. So the goals are specified with respect to desired configurations for the objects in the scene. A lot of work in NAMO and rearrangement planning, and NAMO does use simulators to evaluate the result of robot actions, but there's a separate line of work on simulation-based planning that deals with the problems where the transition dynamics for robots are computationally expensive to compute. So if it's difficult to get the result of the robot executing an action or some sequence of controls, you might want to call a simulator to give you the end state of the robot. But because it is time consuming to do so, you want to be judicious and efficient in when and how you use the simulator. And these algorithms deal with coming up with that strategy of being more careful in your use of the simulator. In our work, we focus on the NAMO domain, and we work in 3D workspaces. So a lot of the previous work has focused on just planar problems, which we build on and put everything in our 3D workspaces. We're also going to focus on non-prehensile rearrangements of the scene, which is different from what was done at the beginning, where you assume that the robot will grab these objects and they become rigidly attached to the robot. Then you can put them down somewhere else. And we have a bunch of complex interaction constraints, which make the search for a solution pretty difficult. So because you can't just arbitrarily hit objects aside, you have to be careful in how you manipulate them. A lot of actions can be invalid if they violate these constraints. And the key theme in both the works we completed so far is that we can use a lot of domain knowledge about the workspace, about the objects, about the robot, to be selective in which actions we evaluate in the simulator and when we evaluate them, which reduces the amount of time our planning algorithms spend coming up with a solution. So I'll begin the rest of the talk by just establishing what domain we're focusing on. So I'll give you details about the manipulation among movable objects domain. I'll go on to talk about the first bit of completed work, where we looked at workspaces that have relatively large object free volume or not that much clutter in the workspaces. And then we relaxed some of the assumptions we make in that work to focus on more cluttered and more constrained workspaces for the robot. And finally, I'll go into the remainder of the work in this thesis on coming up with some theoretical guarantees and then generalizing it to more challenging planning problems. All right, so this thesis focuses on the domain of manipulation among movable objects. The only difference between this and NAMO, where navigation among movable objects is the task that's given to the robot. In NAMO, the robot's just told to go from point A to point B, and it's allowed to reconfigure the environment. In NAMO, the robot is supposed to manipulate an object. So in our case, it's to grab something from the workspace and come back out with it. Our robot is a 7 degree of freedom PR2 arm, and we fix its space. So we're not doing full body manipulation. We're just doing arm planning for now. And we look at tabletops and enclosed shelves in 3D as our workspaces. The objects are a mixture of movable and immovable objects. This distinction is known to us prior to planning, and because they're in 3D space, we keep track of that configuration or that pose in SE3. So we keep track of their XYZ coordinates and their rotation, angles of rotation about 3 axes. We do assume that we have full knowledge of their models. So we know the objects' dimensions, masses, coefficients of friction, and we know where they're located at the beginning of planning so that we can then figure out how to manipulate them. And each of these objects are associated with some constraints that you have to satisfy while searching for a solution. So the immovable obstacles cannot be touched by either the robot or any movable object. The movable objects can be touched, moved, pushed, rearranged, but there are constraints on how far you can tilt them. They can't fall over, they can't fall off the shelf or the table, and you can't just hit them in order to move them aside, which you might think does not happen, but accidentally, of course, you can make your robot do something like this. Definitely not something you want your robot doing. So with that, the problem statement in this domain is just very simply to find a path of valid states that achieve whatever goal you specified. So if you're trying to grab an object, the goal is specified as a grasp pose for that object. We're not solving the grasp planning problem in this thesis. If you're coming back out with an object, then it's some whole configuration that you have to achieve. And validity of the state is defined with respect to the interaction constraints associated with all the objects in the scene. So something naive that you can do to find a solution is give your robot a very simple action space. So say that it can change each of its joint angles independently of the others. This action space can let you create a graph, which you can run your favorite graph search algorithm on. So you could run A star from the start. The issue here is that because you're in a domain where you have to rearrange clutter, you might have to simulate every action that interacts with the movable objects in the scene. And so because you want the result of that action to tell you what configuration the world achieves as a result of that action. Remember, you're searching this space that grows with the number of movable objects. You could do something better than that and be lazy about when you simulate these actions. So laziness just refers to the fact that you execute the most expensive part of your planning algorithm, in this case, simulating it, which is the most time consuming, when it's absolutely necessary for you to determine the result of that action. You could bias your search more to focus more towards the goal and run a weighted search. If you had a bunch of heuristics to give you more information about the planning problem, you could incorporate that in a multi-heuristic search algorithm. In case you're a fan of sampling-based planning algorithms, you can replace the first line with your favorite RRD style algorithm. So we compare against something called k-piece, which is very similar to RRD. It's just a little bit more intelligent about how it grows its tree. The issue is that you have to simulate all actions in order to determine, one, how the state of the world evolves, and two, whether or not you violate any interaction constraints. And because you're searching this large space that grows with the number of objects, you end up simulating a lot of actions, which takes a lot of time, and it's just not a good idea to simulate everything because it'll take the planning algorithm far too long to find a solution. So if you run that lazy weighted multi-heuristic A star search, it looks like this. So in this case, the only object that needs to be rearranged is a stalled cuboid that's right in front of the yellow object of interest. But the naive algorithm simulates all actions that interacts with this object. And so because there are a lot of these actions, it spends more than 30 minutes searching for a solution. So if I'm just sitting on my couch waiting for my robot to bring a beer, I don't want to wait for more than 30 minutes probably before it tells me that, well, it's going to take me longer. So the takeaway about the domain is you're searching a pretty large space for a solution, and it's extremely time consuming to simulate everything. But we can be better about this if we know we exploit some characteristics about workspaces where there's not that much clutter and there's relatively large object-free volume. So for these workspaces, our planning algorithm is able to figure out a way to just near the goal which is the grass post to the box of Cheez-Its, figure out how to push these objects aside that are in my way so that I can go and grab the box of Cheez-Its. And when you see the robot approaching the box of Cheez-Its and then just slightly nudging these the movable clutter aside, it's executing something that we call adaptive motion primitives, which form the basis of our algorithm for these workspaces. So adaptive motion primitives are actions that are dynamically generated during the search, and they're generated in a way that they terminate at a valid goal state. So if the goal is specified as a grass pose, they're going to end at that grass pose, or the robot arm will end at that grass pose if it executes the action. If you're coming back out with it to some home configuration, that will end at that home configuration. These actions are straight lines in the configuration space of the robot, which means that they change all 7 degrees of freedom along the same action compared to that simple action space I described earlier, where only one joint angle is at a time. The video is just running through some random examples of adaptive motion primitives I've generated for random grass poses in this workspace. But the good thing about them is because they change all joint angles, they lead to a much wider variety of interactions with these objects, which lets us do things like approach the thing we care about grabbing and then carefully push the things that are blocking us from grabbing it aside, just enough so that we can execute the grasp. So pictorially, adaptive motion primitives are defined with respect to a parameter delta, which creates a ball in configuration space around some goal configuration xg. And as always in this domain, we have some movable objects and immovable obstacles that we care about. During your search towards this goal configuration, you might end up inside this delta ball at some states x1 to x4, and you can draw straight lines to your goal configuration xg to get adaptive motion primitives a1 through a4. And looking at this image and knowing what you know about movable objects and immovable obstacles might give you an idea about which of these actions are valid, invalid, and which ones you need to simulate, which forms the basis of why this algorithm is actually efficient in this domain. So when I said earlier that it takes about 30 milliseconds to collision check an action versus 1.5 seconds to simulate it, I was talking about these adaptive motion primitives. And we want to use as much information as we can get from the collision checker to be more efficient in our use of the simulator. So in this case, we have a 2-phase action evaluation scheme that first collision checks all actions against all objects, which is much cheaper to do in terms of time spent. And we then only simulate actions that collide with movable objects. So in this image on the right, actions A1 and A2 collide with immovable obstacles, which is information we get from our collision checker. So we can immediately invalidate them without ever needing to simulate them. A3 doesn't collide with any object at all, so we know that it's valid, and we don't need to simulate that either. A4 is the only thing we need to simulate because it collides with only movable objects. And we need to simulate it so that we can determine whether or not it violates any interaction constraints. So you can go further and say that we only simulate adaptive motion primitives in this domain because if we find one that's valid, we know that it ends in the goal state that we've specified. And then it remains for us to find a path in only the robot's configuration space that's collision-free to the start of that adaptive motion primitive, because then we can just execute the adaptive motion primitive that we determined to be valid in simulation to reach the goal configuration we defined. So again, I'll walk you through a simple example where you have some start and goal configuration you've given for your robot, and the images are just showing you an example of what that looks like in the 3D world we live in. On the right, I'm going to walk you through what happens in the configuration space. So XS and XG are your start and goal states. You have movable and immovable objects, as always. The naive algorithm that I showed you earlier essentially executes a 3D search towards the goal configuration. It ends up at a state B, where it sees that a lot of my actions are now colliding with movable objects. So I need to simulate all of them to determine validity. And as you saw in that video earlier, it simulates a whole lot of actions before it will find a sequence that pushes object O2 aside, and then it can proceed on its way. It'll spend a lot of time simulating things around B. In our case, because we restrict ourselves to simulating all the adaptive motion primitives, we'll find this collision-free path that bypasses all contact with objects. ends up at some state u inside that delta ball around the goal configuration, and then we start simulating the adaptive motion primitives that the search generates. If we find one that's valid, that doesn't violate any constraints associated with O3, say in this case, then we can just concatenate it to the collision-free path that we found in the state u, and then we have a complete path from start state xs to the goal configuration that we've defined xg. So we ran a bunch of simulation experiments with this algorithm in tabletop and refrigerator workspaces. We randomly initialized some objects from the YCB data set for the robot to deal with, and we're going to compare against two state-of-the-art baselines. The first is a search-based planning algorithm, selective simulation, which goes back and forth between a planning phase and an execution phase. It plans path, it then executes it in the presence of all objects. If that path violates any interaction constraints, the culprit of that violation, the object with respect to which the constraint was violated, is identified and added into the planner as consideration for the next iteration when the algorithm will start simulating all actions that interact with that object. And then it goes back and forth until the path is valid in the execution phase. KPs is a sampling-based algorithm, which is essentially just RRT, except that it's more intelligent about how the tree is grown. And it maintains some sort of exploration score to guide its growth of the tree towards the goal. The video is going to run through some examples of our algorithm grabbing objects in somewhat cluttered spaces. But the more important thing here is that even though we restrict simulations to just adaptive motion primitives, for these workspaces, it's not a limitation because we end up solving the vast majority of problems. So we solved 99% of tabletop problems and 93% of refrigerator problems, with the added benefit that we're only simulating some adaptive motion primitives, and we're only searching in the configuration space of the robot. So our planning times and simulation times are much lower than these two baselines, somewhere between 3 to 20 times lower. And you can put this on the real robot. It does pretty well. I think we ran 39 runs, and 7 of those failed. But remember that any solution that the planner returns had to have been valid in simulation. So if it fails in the real world, it's because there was a mismatch between what was initialized in the simulator and the scene in the real world. In most of the cases, these failures were due to differences in the coefficient of friction that I initialized in the simulator and the true coefficient of friction. So there was some error in me manually measuring the coefficient of friction. So the simulator thought that an action was going to be valid, but in the real world, it made something follow. But the takeaway is that in workspaces that have relatively large object-free volume, you can get away with just avoiding contact until you're close enough to the goal, and then you can rely on simulating actions that you know will take you to the goal. So it just you just need to find one of those actions that's valid because you know that it will end in the goal state. But if you go from those workspaces that look like this, that have a lot of empty space, to more cluttered and more constrained workspaces like this, which is a pantry shelf in my house, actually, and you want your robot to grab the bottle of balsamic vinegar, say, you have to think about how hard it is to get close enough to this bottle to grab it, which is not that straightforward because there's all this clutter in your way. Even if you could get close enough to be able to grab it, grabbing it is difficult itself because on your way to that bottle, you might have pushed something in front of you and you'll end up grabbing the wrong thing, or you might be pushing up against something else that will stop you from grabbing the bottle. But say you manage to grab the bottle, coming back out with it is another difficult problem because on your way out, you might make contact with another object and make it fall over or fall off the shelf. And these are things that you do not want to happen in this domain. But if you had a robot that could push this bottle of rice vinegar off to the left and then push the bottle of soy sauce off to the left, it's then cleared up enough space for itself to go and grab the bottle of balsamic vinegar, which is the task that you assigned it. So the thing to note here is giving our robots the right action space for the domain that they're in or for the task that they've been assigned is important because Previously, the robot was never allowed or did not know that it could execute these push actions, but now we're giving it this ability. And you could add these push actions to the naive algorithm that I presented earlier, where we tell it that if you're close enough to a movable object, you can try and execute these pushes to rearrange the clutter, which in practice doesn't do something that's all that different from what the original naive algorithm with that simple action space was doing. Another baseline that we came up with is more informed one, where we throw up this GUI to a user. It's a 2D image of the same scene, and we tell the user to draw some paths that the robot can track in order to get to the yellow object of interest, and at the same time indicate some locations along this path where the robot should consider executing a push action to rearrange the clutter that's in its way. So you can get a bunch of these paths, and they're more informed in that the user has thought about some 2D trajectory for the robot to take that takes it to a location where it's good to execute one of these push actions, in the hopes that this sequence of tracking the 2D path and then executing a push action leads to a rearrangement of the scene that clears up enough space to grab the thing you care about. The problem with both these baselines is that as they're searching for a solution to grab the object of interest, they're not reasoning about good ways to rearrange this clutter. So they're just searching over all possible actions that they can execute in the hopes that one of them actually rearranges the clutter in a good way. But it's not informed by what the task of grabbing the object of interest needs. So I spend a lot of time drawing these paths and watching these algorithms not really do a whole lot. And I came up with the idea that if I just imagine these movable objects as tiny little robots themselves, if I say that they're allowed to move of their own agency, I actuate them, and I can run a multi-agent solver to tell me how they should move so that the robot can go and grab the yellow object of interest. Which is a weird idea, and we're gonna work through some examples, but for this multi-agent abstraction, the agents are the PR2 robot, of course, but also the objects of interest and movable objects. The goal for our PR2 is just to grab the yellow object of interest and come back out with it. For that object, it's supposed to stay in place until it's been grabbed and then track the end effector of the robot on its way out. The movable objects are just tasked with avoiding all collisions, because collisions in this abstraction would mean that there's penetration between objects, which is not physically possible and therefore not allowed. The robot, the PR2, is just going to plan in with the simple action space of independent joint angle changes, and these objects are going to move on a grid from the shelf that they're placed on. So in this weird, fake, abstract world where we've actuated the movable objects, what we get from solving the multi-agent problem is that if they were truly actuated, then the robot path that we've computed solves the mammoth problem. So if you take this workspace, what we do to solve the multi-agent problem is we project it down to 2D first, and then we run a solver for the robot path to grab and come back out with this object. For this robot path, the multi-agent solver then moves these objects aside in a way that that path is feasible. It does not collide with anything. So as you see, the robot's, the PR2 arm's projection is executing the path that it computed in the absence of all movable objects. And given that path, these objects are moving aside to let it grab the yellow guy. The issue, of course, is that these movable objects aren't truly actuated. So we have to use the thing that is the only thing that's actuated, which is PR2, to make them move in the way that the multi-agent solver says they should. So we do this by computing a bunch of non-prehensile push actions, and we're going to take this mammal workspace, we're going to project it down to 2D again, and we're going to get a multi-agent solution. So we computed a robot path, and for that robot path, the multi-agent solver says that the circle object needs to move, and then this rectangle at the bottom needs to move a little. Given this multi-agent solution, we go back to our 3D workspace, and we sample a bunch of push actions for these objects, which are now a cylinder and a cuboid respectively. We're going to plan a path to the start of these push actions and simulate them all, because we still need to ensure that the actions the robot takes are valid with respect to the interaction constraints. And we're going to select the best push as the one that most closely replicates the object path that was returned by the multi-agent solve. So for this example, we start by sampling some pushes for the cylinder, and we're going to simulate them all to determine whether or not they're valid. In this case, the push that it just executed is the one that's going to end up being the best push. But we simulate all of the ones that we've sampled so far, and having found a good push for the cylinder, we can then go and start sampling pushes for the tall cuboid at the near edge of the shelf. And I think this one here is going to become the best push. It does tilt the cuboid slightly, but it's within allowed limits, so that it doesn't violate any interaction constraints. At this point, the multi-agent solver says that you rearrange the scene satisfactorily. So the original robot trajectory you computed will succeed in grabbing the object of interest and coming back out of it. So in our algorithm, we have a robot arm planner embedded inside our multi-agent solver. We solve for a robot path in the absence of all movable objects. We project it down to 2D, feed it to the multi-agent solver, and ask it to give us object paths that conform to the robot trajectory that we've computed. These object paths are fed to our non-prehensile push planner, and we sample and simulate a whole bunch of pushes for all of these objects and try and select the ones that most closely replicate the multi-agent solution. And this loop keeps running until the multi-agent solver says that there are no more rearrangements that you need to execute. You pushed objects aside enough so that you can go ahead and execute the robot trajectory, and you won't collide with anything on your way to grabbing the object of interest. Again, we ran a bunch of simulation experiments in workspaces that I showed you images of so far, and the video is just going to run through a few examples of our algorithm solving these problems. So this first scene is actually the one that you saw the naive algorithm struggling at the very beginning of the talk. And for our experiments, we compare against the algorithms in the previous section, which I call STAMP. The two baselines that use the push actions, so the naive, lazy, weighted, multi-heuristic A-star search, and the UI-based baseline, where I've drawn some paths for the robot to consider. And we're also going to compare against selective simulation, which is the search-based planning baseline. And as you can see, we solve 85% of the problems in this domain, whereas the other algorithms don't solve that many. So the UI-based thing does solve 56% of these, but that's still not that good in my opinion. And because we are informed in which rearrangements we consider by the multi-agent solution, we are much more efficient in our use of the simulator compared to these other baselines. So on average, it takes us about 78 seconds of planning time to come up with a solution for these domains, whereas the other baselines solve much fewer instances and take longer to do so. We'll move on, and the thing to remember here is that, oh yes.
What happens to the other 50%?
You just timed out. So there was a 5-minute timeout that I gave to the planner, and it just ended up simulating more than, yeah, it just timed out.
Okay. It doesn't happen in certain configurations, or
Well,
it's just something that happens?
no, so it depends. In some cases, it can be, depending on how the objects are placed, it can be difficult and time consuming to sample pushes. In some cases, it's that the objects are precariously placed, and so the pushes that you end up sampling will make them fall over or will violate some constraints. So it's just a matter of you not being able to find a good push in the allotted budget, because the constraints make it tricky to carefully push these objects. The thing that I'm not parameterizing the pushes with is the speed of execution of the simulator. That's fixed. So that's something that I could include, but not remote. So in this case, we're directly informing our rearrangement planning with a solution from the multi-agent planner. So it tells us which objects need to move and how, which is a lot better for us when we start sampling pushes to consider. But there's still a question of whether or not we are complete in this algorithm. So the first bit of proposed work addresses this question of completeness of the algorithm that is presented. Completeness is just the property that the planning algorithm will return a solution to you if one exists, and it will return failure if there's no solution. For search space planners, completeness is defined with respect to the graph that they're searching, because any solution that they find has to lie on that graph. In our case, we have this back and forth between an ARM planner and a multi-agent solver, where we try to come up with a multi-agent solution for a given robot path that we've computed. And then there's also this aspect of taking that multi-agent solution and trying to replicate it in the simulator with these push actions. Both of these introduce a notion of incompleteness that can be addressed by introducing some form of backtracking. So you can get some feedback from some failure mode and try and do something else, so that at the end of the day, you end up spanning the space of all possible solutions that exist, which if you can do that, then you'll be complete. So the first bit, where we take an ARM plan, project it down to 2D and feed it to the multi-agent solver and ask it to come up with a multi-agent solution to the abstract problem we defined. The projection step does introduce some approximation errors, but that's easily alleviated by just running the collision checker in 3D. And it has the added benefit of allowing us to instantiate concave objects in our workspaces. But the bigger issue is that the multi-agent solver essentially treats that robot path as a dynamic obstacle. And it tries to move the objects around it in a way that they avoid all collisions. But that might not be the case. And there might be a multi-agent solution for a different robot trajectory. So what we need to do is go back to the robot ARM planner and tell it to come up with a different trajectory. So I'll walk you through a quick example, but suppose you came up with some path pi naught that the multi-agent planner failed to find a solution for. You can go back to the robot ARM planner, instantiate a whole bunch of independent planning problems that say, in this one, the robot can't be at state x1 at time 1. In this one, it can't be at x2 at time 2, so on and so forth, for all states in the path that you just found. You can then solve for each of these planning problems. You can get a new robot path that satisfies the constraint, feed it to the multi-agent solver and ask it for a solution. If it fails, same thing. Go back to that, add more constraints in new independent planning problems, and start satisfying these constraints one at a time. What you get as a result of this is this back and forth of adding constraints and the multi-agent planner failing will make the ARM planner go through all possible robot trajectories that exist in this 7-dimensional configuration space of the robot. And if for none of them, the multi-agent planner says there's a solution, then there is no solution. The other bit of incompleteness arises when you take the multi-agent solution and compute pushes that try and replicate these object paths in the workspace. There's no reason to expect the robot to be able to very precisely move the objects like the multi-agent solution says they should. And you might end up in a weird dead end where you've pushed an object into a configuration from where you cannot grab the object of interest that you want to, but also that for any robot path, the multi-agent planner says there's no solution. So in this case, you need to go back to a previous rearrangement and ask the robot to do something else to push the object in a different way, or ask the multi-agent planner to make that object move in a different way. But introducing both of these notions of backtracking will end up in a planning algorithm that searches over all possible solutions and should be theoretically complete, but that's the first bit of proposed work that I want to address in this thesis. In the second proposed work, I'm planning to think about whether or not we can extend this notion of a multi-agent abstraction and simulation-based planning to other domains, specifically that of assembly or disassembly. This is an image of a domino puzzle that's made up of these different colored pieces. And the task for the robot is to either put it together in that of assembly or take it apart if you're disassembling the structure. And if there's gravity acting on the scene, you need to think about why we need physics-based reasoning and what the multi-agent abstraction looks like. So the reason we need a simulator in the loop is to tell us whether or not any sub-assembly that the robot creates or generates as part of its assembly or disassembly sequencing is stable or not. You don't want things falling apart under gravity. And so that simulator in the loop will be able to tell you whether or not particular structure is stable. Also, if you want to put parts together or pull them apart, they shouldn't be constrained in their motion if you prefer that to happen. The multi-agent abstraction is very similar to what I just presented, where you can think of each of these pieces in the puzzle as a small little robot of itself, and then define their goals with respect to their position in the assembled configuration or the disassembled configuration. And you can run that multi-agent planner, which will tell you that for this specific structure, if you want to disassemble it, these pieces highlighted in green can be moved by the robot. But validating these actions in the simulator would then tell you that this L-shaped piece in the bottom left should not be moved by the robot because it will leave the blue and pink pieces on top of it unsupported. They'll fall down under gravity, which would violate the interaction constraints you've defined in this problem. So that's not something we want to do. The second bit of proposed work then is going to essentially formalize all of this into a planning algorithm that uses a simulator in the loop and a multi-agent abstraction to guide the search for a solution in assembly or disassembly planning. And finally, everything I've talked about so far assumes that we have perfect models of these objects. But in the real world, when you run things on the robot, there's perception uncertainty, which introduces errors in object localization. And there are almost always modeling errors, where you might not know the dimensions of the objects accurately or their masses or coefficients of friction. So we need to think about how do we make these algorithms where we push things around robust to specifically uncertain masses and coefficients of friction, because that changes how these objects move as the robot pushes them. And there's some work in MAMO planning that addresses uncertainty, but it's focused a lot in the past on state uncertainty. So essentially localization errors in these objects. There's some work that tries to use model predictive control to execute parts of trajectories that the simulator thinks are less robust. And parallel to this, there was this paper that tried to estimate the mass distribution of objects by pushing them around and seeing how they move, in the hopes that you can then use this computed mass distribution in your planning algorithm. But we still don't have a good solution for MAMO planning problems that are able to account for uncertain object masses and coefficients of friction specifically. In the case when you're pushing them to rearrange them, that's important. And that's the third bit of proposed work. So the first thing that I will do once this talk is done is run a bunch of experiments with the real robot. You've seen 2 videos that I generated for the talk, but I need to run a more thorough quantitative evaluation of that algorithm on the real robot. And as a first step towards making the algorithm complete, I'm going to remove the projection step to 2D and just run a collision checker in 3D. The bulk of the sprint is going to be spent on introducing the 2 notions of backtracking that I talked about to make that algorithm theoretically complete, and then go on from there to formulate the multi-agent planning problem for assembly or disassembly planning. Over the summer, I'll work on the algorithm that uses that abstraction and a simulator in the loop to solve assembly planning problems or disassembly. And then I want to quantify the performance of our algorithms with respect to uncertain object models. So I just want to get a sense for how badly we do if we don't know an object's mass accurately, or if we put it on a different surface and the coefficient of friction changes. I want to quantify those errors. Over the fall, then the task is to make the MAMO planning algorithms robust to these uncertain object masses and coefficients of friction, and then write and define my thesis in the fall, which is a relatively aggressive timeline, and there's a lot of work on this slide, but if it gets stretched to the spring of 2023, that's okay. And maybe even along the way, my girlfriend's cat will decide to help me when I'm trying to get beer out of the fridge, which didn't happen when I was making this presentation. But all jokes aside, Max and Sahil are great people to work with, and a lot of the work that I've done in this talk is thanks to their help and support. So I'll leave you with some of these takeaway messages, and I can take any questions.
All right. All right. Well, first of all, I'm very happy for the physical plugin. Okay, so the typical model is that the committee first asks questions, and then the audience goes after that. In particular, within the committee, we usually start out with a person who is an external member. In this particular case, of Mehmet. So, Mehmet, are you okay to ask questions first?
Sure, yeah, I can do that.
All right, go with you. Go ahead.
Cool. Thank you, Dhruv. This was great. Can you hear me clearly?
Yeah, I can.
All right, perfect. So I want to start with basically a clarification question, which is in the part one with the adaptive motion primitives. And also in the second part, I think the second part I had answered, but in the part one, can the goal object move? Is it allowed to move or not?
No, the goal object is for all intents and purposes an immovable object.
Okay, and is that an important can you, without too much effort, fix that in your algorithm? Why does it have to be fixed?
It has to be fixed because a limitation of the planning problems we're instantiating is that the goal for grabbing that object is defined with respect to a specific pose of the robot arm. So I'm not planning to solve the grasp planning problem. So I assume that the grasp pose is given to me, and then the grasp maneuver itself is just a hard-coded thing. So if the object that I want to grab moves, then the grasp that's been defined or the pose that's been given to me might no longer succeed in grabbing that object. So I need to think about for any new configuration that object ends up in, what grasp pose the robot needs to achieve so that it can successfully grab that object. Currently, that's not something that the algorithm handles, but if you had a grasp planner as part of the loop, then you could do that, and you could reason about things where you want to grab an object that is currently not graspable, but you can slightly nudge it in a way that it then becomes graspable. So that's not something we do right now, but you could incorporate that.
Yeah, I mean, I'm not asking for to do grasp planning, because it may be that you're given a grasp, but the grasp can be given relative to the object, right? So it may be a fixed pose though in the object frame, and so you will need to track how the object would move, but the hand pose would be fixed with respect to it. But I guess the reason I'm asking is I was like, when I was looking at the document, that was like it seemed to me the goal object was fixed. So and this confirms that. It kind of conflicts with your key assumption in that section, right? Which is that you only want to have physics-based interaction at the end when you're really close to the goal object, right? That is your assumption. But you also have this assumption that nothing should touch the goal object. There shouldn't be any physics interaction near the goal object. So these are kind of contradicting with each other. And I feel you probably need to plan operations where nothing touches the goal object. You push objects out of the way, but only if they are pushed sideways things work. But if they go and contact the goal object itself, then so that seems to be kind of conflicting. So it would be good to think about how to resolve that conflict, and if the algorithm can actually accept the goal object moving, I would say.
Yeah, I think so. Like you said, if the goal was defined in the object's frame, then you could allow it to move and keep track of its state as well. In which case, yeah, you can definitely have that object interact with other objects or with the robot, and end up in a configuration where it's displaced from its initial location, but you're still able to grab it. In the first section, that was not a huge issue because there are so many ways for you to get close enough to that object that if you sample a bunch of adaptive motion primitives, most of them, and in fact, I think when we randomly sample, like something like 70% of them actually are valid. So it's just a aspect of the domain or the workspace in that section that lets us get away with this assumption essentially.
Related to this, so are you including the finger joints in your planner in the first part? The finger, the grippers, the two joints?
No, so, well, in a sense, yes. So when we execute the adaptive motion primitive, it gets to the grasp pose, it then executes the grasp maneuver and lifts the object up. So that all of that is simulated to check for validity.
So because in the videos, the fingers do a lot of work, right? You go there, what I realize is that most of the grasps you do, the fingers open up and they push the two objects to the side. So that bit is within the adaptive motion. It's in the physics simulation, right?
Yes, it is within the physics simulation. It's technically not in the adaptive motion primitives because that bit's hard-coded for any adaptive motion primitive, but it is simulated to determine validity.
Yeah, because I think, you know, the heavy use of the fingers to push things sideways is related to the problem of the goal object being fixed, because, you know, then the only way is to push things sideways, and that I was thinking maybe is the reason for those types of actions. Okay. I'm sure you must have thought of this, or maybe you even tried, like, you know, did you try starting with a small delta, like the bubble in which you do the adaptive motion primitive, starting with 0, and, like, you know, if you can find a collision-free path all the way, why not? And then making it larger and larger as you cannot.
Yeah, so the part of that algorithm that I didn't present in the talk is we actually simulate or sample and simulate the adaptive motion primitives before planning even starts. And if in that time period we determine that one of the adaptive motion primitives is valid with just the use of the collision checker, then we can just find a completely collision-free path, which is super fast because nothing will ever get simulated and we'll just end up at the start state of that adaptive motion primitive. The thing where you're talking about increasing delta over planning, it's not something that I've tested algorithmically. It's something that I've tested like kind of when I was parameter tuning. So it's a fine balance between having a small delta versus a large delta. And it's something that we just experimented with to come up with a value. In either case, if you have too small or too large a delta, you can run into issues. So there's no good way to determine what delta should be, but I haven't actually tested it algorithmically where we start with something like delta equals 0, and then if we spend some amount of time and fail to find a solution, increase delta, rerun planning, that sort of was never an issue because we had this step where prior to planning, we would sample and simulate adaptive motion primitives and then use them as attractor states in our multi-heuristic search.
Okay. So moving on to the second part with the multi-agent planning, but like connecting it to the first part. So one thing that I really liked about the part 1, where you do the adaptive motion primitives, is I interpret it as you think about the complexity, computational complexity of the transition model, sort of like, you know, in some parts of the space, the transition model is expensive. You need to simulate pushing things. But what you're saying is you can actually, if you can go to slide number 21 or 22, those 22 then maybe. Yeah. So if in this, for example, in the first part of your trajectory, you take a longer path. I mean, you can go through the blue object, right? Because it's movable, and it would be a shorter path. but you take the longer way just to make your transition model, because the transition model is cheaper on the longer path, and you don't want to go to shorter during execution, because it will make your planning problem computationally more expensive. So this is great, and you can't think of you do it in a 0-1 way, like you either move through collision-free space or go to the physics engine. But you can even think of cases where if you're pushing 3 objects together, it may be computationally more expensive versus pushing 1 object. So maybe you may want to physically simulate pushing 1 object only, not pushing 3 objects simultaneously, and so on. So this was, I feel like, the key thing in part 1. But when you go to part 2, I think you start by ignoring all the objects and generating a robot motion to reach the goal object. And then you take that and give those objects to the multi-agent planner to move those objects out of the way. So I feel like, there was this conflict between the 2 parts, in the sense that, what you were proposing to do with where you were benefiting in the first part, which is avoiding parts of the state space where you need to physically interact with objects. When you start with ignoring all the objects, you may be going through 5 objects that you need to move out of the way because you ignored everything. Whereas on the side, you may. Sorry, I guess I asked 2 long questions.
We'll get to Chris in a bit. You can ask the question.
Okay, cool. So, but I think you got my question. Is that right?
Okay.
Yes.
Without going too much into implementation level details, this aspect of bypassing collisions with objects, if possible, shows up in the second bit of work as well, because when we're actually planning for the robot trajectory in the absence of all objects, the heuristic that we're following is accounting for their presence, in a sense. So it's trying to take us as much as possible through regions of the space that are not occupied by any object, and the multi-agent planner will only move those objects if they collide with the robot path. So it's never something that I'm explicitly enforcing on my planning algorithm, but these 2 things do take advantage of any free space that's available. So the robot tries to stay as much as possible in space that isn't occupied by any object, movable or immovable. And the multi-agent planner, of course, only moves them if they truly need to.
Okay. Thank you very much. These are my questions. Thank you.
Thanks so much.
Thank you very much for the questions. All right, so I think Chris is all ready to go and ask questions. So we'll move to Chris.
Okay, this is a very interesting piece of work and leads to lots of questions. And I'm happy to deal with some of them now and some of them later when we chat. One of the issues I'm really interested in is what are in legged locomotion, we finally figured out simple models that allow you've got a good example here where MapF is in some sense a simple model that allows you to improve planning. What other simple models could possibly work? I thought of one where instead of actually moving stuff out of the way, you had a magic wand that made obstacles disappear. Any thoughts on that?
So it's much easier for me to address the magic wand than it is to address what other simple models we can construct. The aspect of the magic wand that you're talking about is very closely related to that last question that Mehmet asked. The algorithm that I presented, we do pretend as much as we can get away with it, that these objects don't exist, which is why the robot is able to come up with a path that, or that's not why, but the robot comes up with a path that tries to avoid contact as much as possible so that the objects in some sense move as little as they need to. So that's the first part of that algorithm where we plan for a robot path in the absence of all objects. You still at some stage need to deal with the fact that the objects are not going to magically vanish. So if you imagine that they're not there and plan a path that goes through them, executing that path will almost never be valid with respect to the interaction constraints. So you do need to account for how that object that you pretended was not there needs to move, because the path that you've computed is certainly not going to move it in a way that's valid. So you need to do something on top of that, which is essentially what we're getting out of solving the multi-agent problem. It tells us that, oh, look, we first pretended that this wasn't there, but now that it is, I'm going to tell you how it needs to move so that you can execute the path you computed. Now, the other question about whether there are other simpler models that we could use to solve this planning problem, I don't have a good answer for that. One thing that you could do is come up with an algorithm that gets close to objects or somehow identifies objects that need to move, gets close to them, and focuses some of your search budget on pushing them aside or relocating them, or perhaps even grabbing and putting them down elsewhere. All of that is connected to the idea of giving your robots the right action space. And there's probably something you can do there where you run a search that's searching for a path to your object of interest at the same time that it's spending some planning budget on pushing things that are in the way of that path. You could also formulate some sort of optimization problem that tries to create a tunnel around the path that you've computed for the robot by pushing these objects out of that tunnel, and then come up with a trajectory that snakes through this in a way that those objects are pushed outside. But again, those are just things that I've seen in papers, but are either tested on simpler planning problems or take a lot of implementation effort.
So what the MapF thing is doing for you is in some sense telling you out of the infinite world state, what is relevant.
Yes.
And, it essentially allows you to construct a much simpler and smaller problem. It would be great if you could figure out how to answer this question, what is relevant, for a much wider range of manipulation. Right now, objects are obstacles, but objects could also be tools, like a long pole could extend the reach of the robot. And you could have suction grippers as well as hands. You could have multiple robots. I would urge you to try to find or generalize what you're doing, so you had general stuff to say about a wider variety of planning problems.
I agree, but correct me if I'm wrong. I think what you're getting at is very similar to the task and motion planning problem, where you give your robot access to a bunch of symbols and predicates and allow it to take advantage of these things in order to come up with a solution for the domain that's it. So yes, I agree that there's a lot that we can do if our robots had access to other ways of reconfiguring the environment. And there's probably ways that you could incorporate that into the framework that I presented in the second section. But I think it's very similar to task and motion planning, and that's something that is obviously very related to the algorithm that I presented. So yes, there's room for me to think about things, and I'll look into that.
So your statement that simulation is very expensive and we want to minimize it, obviously screws out, can we approximate simulation in some way that's faster?
Mhm.
And since approximation these days is called learning, that gets you into the somewhat sexier area of neural networks learning, mumble. So I'd urge you to consider doing that as well.
Yes, it's always been in my mind to compare against learning-based approaches. And that's something that I wanted to discuss with you more deeply, because if you go the model-free route and ask a learning algorithm to solve the whole problem end to end, I think that might be too difficult. If you also wanted to work over a wide variety of objects and configurations of the scene and all of those things. There's definitely parts of my algorithm that can benefit from learning, I think, but getting a balance between model-free and model-based for this domain, I think, is important in order for learning to actually shine. And I'm sure that you're the perfect person to talk to about that. I don't know if the whole problem end to end is solvable by learning.
Definitely not. But all we're talking about is make simulation faster.
Yeah. So to that end, actually, I'll throw in a plug for one of Mumad's paper. They did something called parallel that tries to go back and forth between a course simulation and a fine simulation. Pretty cool work. So I think that's a good way of speeding up our simulators.
Your testing paradigm of here, let's do something with YCB objects, a certain number of them, actually plays to a learning approach, because now we know exactly what to train for. YCB objects, a certain number of them.
Mm-hmm.
So it's what you said about, well, I don't know what to learn if I'm doing general stuff. The reality is you're not doing general stuff when you actually evaluate this stuff, and robots don't really do general stuff either. You're tuning your amps and whatnot for the problem you're doing. So you might as well go whole hog and, learn it, specialize as much as possible.
I could, yes, but the end goal shouldn't be something that's limited to the YCB dataset, because that's the only dataset we have access to at the moment. It should be something that is capable of solving general manipulation problems outside of the lab. And the reason we choose to use the YCB dataset is because it exists in our lab, and we have a perception system that can detect and localize those objects.
Generality has been the false goal of robot planning.
I think that's a philosophical question on whether you want generality across tasks and domains, or whether you want generality over instantiations of a particular task.
Yeah, but
I'm
real
talking
robots, typically do a limited range of tasks.
Yeah,
Might as well specialize them for it.
sure, but if you look at like my refrigerator, none of these objects are in the YCB dataset.
Yeah, but your home robot could be specialized for these objects.
Yeah, that's true. I'll give you that bit.
So I think in your thesis, you said backtracking, no problem.
Mm-hmm.
And in the legged locomotion world, where in the hierarchical planning, each level had a different state space. When the high level planner said, do this, the low level planner couldn't do it. there was no way for the high level planner to represent the problem because it didn't have the state space to do it. And so I see the same issue here. I think you're going to have this problem of how do I tell a high level planner that doesn't even know about, angle, orientation, that at certain orientation, the sun is in my eyes.
So in our case, it's not an issue because of the way that we compute the low level solution. So the low level solution, like I said, is treating that robot path as a dynamic obstacle. So if that low level planner is complete in and of itself, then all we need from the high level planner is to feed it all possible robot paths until we get a solution or we run out of paths.
Yes, so you're now saying I might pay a huge penalty in computation time because I haven't solved the backtracking problem.
I'm saying that you could pay that huge penalty in computation time and solve the backtracking problem in the way that I presented, but you don't want to pay that penalty. And so the work that is left for me to do is to be more efficient in the backtracking scheme that I come up with.
So 3 quick questions. I didn't understand for the MapF planner, how you took into account the robot swept volume as it moves these obstacles around.
So that step where we're projecting the robot path down to 2D, that takes care of some of it. It's an approximation, yes, but in the workspaces that I've simulated so far, because all the objects are convex objects, I don't run into instances where that projected representation of the robot arm collides with a footprint of the robot, but actually doesn't collide with it in 3D space.
Maybe it would be useful to include in the examples you look at a 3D packing problem or a 3D unpacking problem. So in looking at your videos, the obvious question is, why is the robot so slow?
It's the trajectory that I'm feeding it. I haven't really optimized the time profile of that trajectory.
Yeah, and these are aesthetic issues. It's also so jerky.
Yeah.
Why can't we have a robot that makes smooth, fast movements?
We can definitely do that with the PR2. It's just that there's the profiler that we do use in our planning algorithm is, I guess, not that accurate with respect to the dynamics that the PR2 is capable of. So what ends up happening is this is an implementation detail, but you run the path we've computed through this profiler and you send it to the PR2. The PR2 is actually capable of executing it much faster. So the controllers that it's running inside can go through those waypoints faster than the times you've assigned to them. And so the jerkiness comes from it constantly applying and releasing the brakes as it's executing this trajectory. You can do better, definitely. It's not something that was a big concern because I was more concerned with the robot being able to push things reliably.
Yeah, I would just urge you to,
Yes, definitely.
in showing your videos, that potentially is the only thing somebody's going to see.
Right. Yeah. I mean, it's been brought up quite a lot in my meetings with Max, where he doesn't like the PR2 being jerky. So something for me to implement once and get it done with.
All right. That was my list. I'm happy to chat later. Whoever's next goes.
Hi, yeah, Oliver. Good.
All right, thanks for the presentation. Really liked it. A couple of clarification questions to begin with. For toppling, is there a constraint that avoids toppling? Or
Yeah, so we keep track of their angles of rotation. So there's the toppling constraint is very closely related to the falling constraint. It's just that things can't topple beyond a certain angle.
okay. And you sort of have the UI kind of benchmark where people are sort of giving 2D paths. So how is that being used for the third dimension? Because it seems like you know you need to push low to avoid toppling.
Right. Yeah. So it's that height is something that I've fixed to be high enough that the whole arm can enter the shaft. So I'm not changing the roll and pitch angles of the end effector. So if that arm is entering straight on, then whatever room it needs to be able to do that is the height that I've fixed, which is, yeah, it's just trying to move along the plane that's as low as possible without running into the shaft for the table. It's not something that I've tested a bunch of values for.
You mentioned early on in your proposal that you have like that you could potentially use more dynamic kind of behaviors. Are there any challenges to that, or is it just a matter of like you didn't need to use them at these kind of times?
No, so you can easily incorporate them in this framework because all you need to do is parameterize those actions and execute them in the simulator. The simulator will take care of telling you whether they're valid or not. So I just never needed them because I didn't see any reason or situation where I would need to hit something dynamically in order to rearrange that.
So you showed a couple times the sort of like the refrigerator setting for yours, and then in simulation. So in simulation, you kind of place them randomly, which is not really how people place things. Right?
Yes.
So have you done any tests on sort of more structure kind of clutter effects of that?
No, I have not. So what I have tested with is, let me go back to an image. Let's see. So in this case, there are 5 immovable objects and 10 movable objects. I've gone as far as having 15 movable objects, but still randomly initialized. So I've never, well, I guess at one point I did try and structure the clutter very early on, but everything that I've tested this algorithm on has been randomly initialized objects. So long as there's room for things to move or space for objects to move into, I think you could still use this. It might get tricky coming up with push actions if objects are very closely packed together and you need to move a duo or a triplet of objects together. But that's not something that I've tested yet.
Okay. I mean, I can imagine that, if there are more clutter like you have in the refrigerator, sometimes it's also that you can move really sort of in like one direction, but maybe not in another direction.
Yeah, definitely. Also, the benefit of more clutter is that tilting constraint can help you. So things that would have made these objects fall over might end up making them rest against objects that are right next to it. So it can be beneficial to you, but it's also trickier because you have to now probably rearrange a bunch of things along your way. And because we rearrange things in a specific sequence, that aspect of being able to move freely in one direction and then being able to rearrange things in another, say, is sort of, it shows up because you clear room for the robot to go and rearrange things that are deeper in the shelf before you try and rearrange them. Because if there's a lot of stuff in front of me here and I want to rearrange something in the back, then I'm probably going to violate some constraints associated with the clutter at the front. So the first thing that happens is these things get pushed aside in a way, in accordance with the multi-agent solution, so that we can then go deeper. But I think this goes back to the other simpler models that Chris was talking about. You could definitely come up with more informed ways for the multi-agent planner to tell you how things should go. In cases where the clutter is more structured, there's perhaps less free space, even less free space.
I wanted to ask about the future work. So first of all, you have this sort of disassembly task.
Mhm.
I guess I'm trying to figure out how difficult is that task? Like, so at this point, you do have prehensile, like you're grasping things from above, right? Or
yeah, for this domain, yes, we would probably allow prehensile grasps.
so am I correct in assuming that like the simulation part of that would just be a check whether it's stable or not? Is that kind of what that boils down to?
That, and in this case, say you wanted to extract the T in the middle, you can't actually do that because there are other things in the way. So
Right, but
which
it seems like some kind of a simple heuristic.
Yeah.
Like, okay, just pick the things that are at the top.
yeah,
Um,
the physics-based reasoning is, I don't think it's super complicated in these cases. But if you had more complicated assemblies, like at some point I was planning to show you guys this slide instead of the one that I presented. So in this case, you might have more complicated physics-based reasoning because the two legs of the chair are not freestanding. So you have to think about how to position them before you put them together. It would vary between the assemblies that we are putting together.
Okay. And would you say it's a very common problem, or is it sort of a?
It's just one where I see the multi-agent abstraction extending pretty seamlessly. So the physics-based reasoning aspect of this is not that complicated. It's just that this idea of applying this abstract space to a different domain shows up here. Alternatively, if you want to stay in that more cluttered pick and place style manipulation, I think this was brought up earlier. If you're looking at packing boxes in a warehouse or packing groceries or something, that's somewhere where you could still allow for non-prehensile rearrangement of things you put in the box so that you can then put something else in the box. I think that that's more closely related to the domains I've looked at so far. So I might swap out assembly disassembly planning for box packing or bin packing, not too set on it yet.
And then so another related work is the sort of idea of being robust to different. You said you're going to sort of run out real world and test it there.
Mhm.
Have you tried just running in simulation with different parameters?
Yes.
And is it important?
Yeah. So I've tried it for the first work that I presented where we were running the rapid motion primitives. In that case, if the coefficient of friction is higher than you think, then things tend to fall over more often, which invalidates some of these actions. So it does affect things. It's just something that hasn't been studied too extensively and those are the parameters that become a lot more important when you start pushing things. So when you instantiate the YCB objects in the simulator, turns out that those meshes don't have a bottom, which makes them behave very weirdly if you initialize the wrong coefficient of friction in the simulator. So it's definitely an issue if you don't tune these values to be more representative of how these objects behave in the real world. But I don't have videos to show you right now or numbers.
But is it really a question of like will it topple or not, or if it doesn't topple, you also get very different trajectories of objects?
Sorry, can you repeat that last bit?
It doesn't topple. Do you also get very different trajectories of objects with the pushes?
If it doesn't topple, then no, it's pretty straightforward. You're able to push it pretty much wherever you want to. And the problem is if it does topple for some actions and not for others, you have to think about where you're pushing along that object and whether the push is straight in the XY plane or if it's maybe slightly going downward so that it stays upright as much as possible, the object does. All of those things will change the trajectory that the end effector or the robot arm takes along the push action. So you might end up with the exact same object paths, but you're achieving that through very different looking pushes, at least in the configuration space of the robot.
Okay, so it does have an effect on those.
Yes, definitely.
All right, I think that's.
So, all right, we had a wide spectrum of questions, theoretical, the practical, the aesthetics. Great. We have a few questions. Number one is, I think there was at some point brought up a question of machine learning. And somehow in your answer, you completely avoided the fact that you did spend some time on playing with that and trying to use it to decide when to invoke a simulator or not. And what you're just ashamed of it.
No, it's just, I mean,
discuss that.
I sort of wrapped it all up in a very hoity-toity answer that said we have to be careful about where we use machine learning. So there are things that I think can definitely be improved with learning. Specific to the second bit of completed work, I think that learning can be very useful in sampling pushes for objects. Currently, it's just a very rudimentary reduction sampling scheme. In the first bit of proposed work, what we tried was we tried two things. One was predicting which adaptive motion primitives are going to be good for us. And we also tried classifying whether an adaptive motion primitive will be good for us or not. So it does work better than random sampling. It's just that in that domain, random sampling was good for us 70% of the time. So although machine learning which adaptive motion primitives to execute might bump that success rate from 7 out of 10 amps that you sample being successful to 8 out of 10 being successful, it's whatever, it's not that big of a game. Because what you're asking your learning algorithm to do is account for, or at least generalize over a bunch of different object geometries, masses, and coefficients of friction. And so for different scenes that look the same, but have different objects in them, it might predict the same action, and it could fail because the objects have different physical properties. So coming up with the right representation for the learning algorithm to be able to generalize across the different physical properties was tricky for us. And we realized that randomly sampling these actions works well enough, so we don't need to bother with the whole machinery of learning those actions. I think that in the second bit of proposed work, or sorry, in the second completed work, there are places where you could speed things up, because like, sampling actions takes me a lot of time right now relative to how long I think it should take me. So I think that learning can improve the space that we sample from, or at least give us a better distribution to sample from. There's also that aspect of me currently fixing how fast the robot moves when it's pushing things around, but perhaps taking information about which object we're trying to push, which we assume we know, can tell us whether or not we can get away with pushing it more dynamically versus more quasi-statically.
Right. The other question is, right now it's a kind of single shot planning. How do you see at some point thinking about interlinked planning and execution?
We'd have to be very careful with that, because you don't want to end up in the the dead end that I brought up in the first bit of proposed work, where you committed to having pushed an object, but there was some execution errors where you came up with not the best push, and now you're in a situation where you have to either push that object back or do something else to the scene in order to be able to proceed along your way. So I think in that case, allowing the robot to be able to rearrange things with prehensile actions would help avoid these dead ends. But you'd have to be very careful about which pushes or which rearrangements you commit to, because if you've committed to a specific rearrangement, you don't want to end up in a dead end where you have to then do something else to see. So I don't have a good idea for how to interleave planning and execution that still gets away with not having to backtrack. But that's the one thing that I would have to be mindful of if I was to interleave planning and execution.
Another question is, so you have one of the proposed tasks on assembly. I guess, the whole business is gonna pick and place, like part of the title. So, why bother with the assembly? And why not just stick with the pick and place and make it more and more complex? It's not like pick and place 100% the robot.
Yeah, that was something that I actually had a discussion with Matt about last week. I'm not tied to the assembly task. It's just one where I see a multi-agent abstraction, but you could also then have, like I said, box packing or bin packing task where it's pick and place and the robot can benefit from non-prehensile manipulation inside that box to rearrange the clutter. All of those things still show up. You still need physics-based reasoning to determine whether a particular packing is stable or not. Each of those objects you can think of as tiny little robots and use the multi-agent abstraction. So I think that's something that we can discuss because I'm not tied to assembly by any means.
The last question is the dependency of the overall approach on in particular the second part, on the discretization of the action space, state space, and I guess on both levels, the full arm planning as well as within map, particularly within map. What sort of how much dependency is restricted or not?
So far, it hasn't been restrictive at all. There are definitely situations where multi-agent planner fails to find a solution because it doesn't have enough room for the objects to get out of the way of either the robot or each other. But currently, my hack for dealing with that is just randomizing the robot's start state so that I get different paths. The discretization, so the multi-agent planner is pretty fast. Like it takes less than a second to find a solution if it exists, or to exhaust all possible things that it could consider doing. So I could definitely go finer on the discretization without really adding too much computational time to my planner. But I think my discretization is 1 centimeter grid on the shelf, which is fine enough that the objects have plenty of time to get out of each other's way if they can. But you can decrease that a fair bit without adding a lot of time to your planning. Doesn't matter. Like I've tried 8 connected and 4 connected. I've tried planning in XY theta space as well. Just pure XY with 4 or 8 connected grids is super fast and works well.
All right, now I'm going to stop here. So let's see if there are any questions from the audience, or for that matter, and if there are any follow-up questions from the committee, that's also fine. Are there any questions either on Zoom or here?
There's one question. So, in your second completed work, that you had a human baseline.
Mhm.
Okay, tell me why your algorithm performs better than the human baseline. What is it that you are doing anything about? What is it?
Yeah, so the core issue is both baselines that I presented are searching for a path by using a heuristic that takes them to the object of interest. The solution necessarily requires you to go against that heuristic so that you push these objects aside, right? None of that is ever something that the naive algorithm makes use of because it's focused on getting to the goal. The UI-based baseline has some of it baked in because I've told it specifically where to push objects, but this was brought up by Oliver's question. There's the extent of pushes that I'm considering is limited because I'm not planning over a bunch of different time defector poses or heights. I'm just getting to that specific location and executing the pushes that I'm allowed to execute. If that push fails, there's nothing else that baseline can do, right? It can't, it's not, I've not written it up in a way that it's allowed to generate other pushes for that specific object. It's limited to the ones that I've added to the action space. In my algorithm, first of all, I don't ever deal with this aspect of needing to go against the heuristic while I'm searching for a path because the multi-agent planner tells me specifically how these objects need to be rearranged. And then for the paths that they take as part of that solution, I can spend as much time as I need sampling pushes. So it's just a better way of doing things.
I have a question. So your core thesis, at least in the first work, is that since simulations are expensive, you have to be strategic about when to call it. What is stopping you from leveraging? Because most simulators nowadays allow you to run them in parallel. So what's preventing you from leveraging parallelization to simulate them instead of one at a time? And does that solve? Does that have conflict with your thesis?
No, so in fact, we do leverage parallelization in the first work, where before planning starts, we parallelly sample a bunch of adaptive motion primitives and determine whether or not they're valid, so that we can then use them in our search as heuristics. During the search, we don't parallelly simulate those actions because we never really needed to. It was super fast without ever thinking about going from 5 seconds of planning time to sub-second planning times. That's not something that ever came up because the things that we were comparing against, the two algorithms, KPs and selective simulation, take tens or hundreds of seconds. You could, again, there are a bunch of things that you can parallelize in the second completed work as well. So you can parallelly solve several multi-agent planning problems for different robot starts and get a bunch of possible rearrangements for you to consider. From there, you could parallelly sample and simulate a bunch of pushes for the different objects that move in these rearrangements that you've generated. So there's plenty of scope to parallelize things, but just not something I've focused on because the problem that we started off with was hard enough to solve already. And coming up with something that is able to solve it was a lot more important than really optimizing that solution.
All right, are there any last questions? No. All right, very good. So we're gonna then stop here. We're gonna take And now with that, we're gonna kick everybody out. Group